So, hello and welcome, YouTube. This is so weird. Okay, so we're going to pick up kind of where we left off with our data structures.
Okay.
And we're going to talk about, I think I left off with our get max and our for each. Let me take a look. You guys did not complete the for each. So, for on line 85. So, for each node in our tree, we're going to call a function. So let me get back into the swing of things. I've usually been teaching for a while by now. So we have our little Christmas tree that somehow looks like a Christmas tree and also a very confusing molecule. So we are going to create this function that loops through and calls itself using our favorite friend, recursion. So this is another recursive function. So the first thing that we have, so we're going to be using a traversal to go down the left and go down the right and call a function on our, and call the current function on our node. So the first thing we need to do is, what's the first thing we need to do, Fatima? Give me a good guess.
Oh, you're asking. Okay.
Yeah, I always ask. I make you guys write most of the time.
Oh, okay. Um, so want to call a function. So we need to make a variable for the node.
We actually have one being passed in.
Is
So the
that
self
self?
is our node.
Okay.
Self is our node. So
Mm.
first thing that happens is we're starting in this node.
So which function are we calling now?
We're working on for each.
Would we be testing an edge case first if there's nothing like no node passed in?
Oh, that's a very good point. You should always check for your edge cases. So if self dot val, so if not self,
Then just return nothing.
just return. Stop the function. No reason to do things. All right. Or, so the another thing that we need to do is we have a self. So we call the function on self.value because we know that we have, the first thing we have is a node, right? We just passed in a node. So we need to call the function on the value of self. How do we get our value from self, Fatima?
We store it in no self.value.
There you go. There you go. There you go. Excellent. So cool. So first thing we do, we are in this node. We've checked. There's a value. Self.value. Awesome. Then what's the next thing we're going to check? So we've got this node.
Did I just lose audio or everybody just got quiet?
Can you hear me?
Yeah, okay, there you are.
Okay. So we have the first node. We've checked. It's got a value. We called the function. Now what do we need to do, Fatima?
Now we want to start doing recursion. So we want to check if the node to the left of this one has a value, and if it does, call for each on it, or run it through for each.
So that's correct. If, now we're not going to see if it has a value. We're going to check that it exists.
Are we going left first?
Yes, we're going to go left. If self.left.
Just leave it there.
Yeah, it's great. Then what do we do?
Then for each self.left
And
dot value.
self.left, no value. Comma function, because you have to continue to pass this function in.
Okay.
And then what else? Well, where else do we look?
We go to the right.
Yes.
Self.right. And we're going to do for each self.right and then pass in the function.
Beautiful. Ta-da.
That's the whole thing?
That's the whole thing.
Ooh.
Okay, so
Oh, wait. Do we need to call? Okay. It's saying it's undefined. Is that? we
self
called
dot
it
for
before.
each.
Okay, cool.
So remember, recursive functions are expensive, but also the best way to traverse the trees in terms of time complexity. But because this is the point of this unit, we do it this way. All right, so we don't need the in order helper.
So just get rid of this?
You can comment it out. Leave some zombie code there.
I'm just gonna comment out.
We are going to use more of our favorite word, recursion. So we have
Somebody say recursion?
recursion.
Recursion. There we go.
Recursion.
All right, so we're going to use more recursion. So we're going to do an in order print. Fatima, what's
Okay.
the order of a tree?
There's the thing at the top, and then there's like, if you want to go in order, we go all the way down to the left, and then we go up a little. As soon as there's something to the right, we go down to the right, then we go back up until there's something to the right again, and then we just keep going until we've gone down. So it's left and then right.
Yes.
Yeah.
Left and then right. So left,
Left.
if
self dot left. Then we run the function again.
Yep.
So it just keeps, so that way it just keeps going down until there's no more self dot left.
Yes, that's right. Self dot left, self dot in order print, self dot left. Now, the weird thing, what do we put in the middle?
Print.
Yes. No, make it even with over here.
Oh, oops.
Remember, Python cares about one thing and one thing only.
Indentation.
Indenting.
Yes.
And now we want to go to the right.
Ava, you might want to drop your mic a little closer to your chin because we're getting your nose breathing.
Okay, yes. Can you hear me better now?
Yeah,
That
but
sounds so much better. Thank you.
All right. So, and that's it. There you go, Fatima. That's the whole function.
Ooh. Cool.
So, there's a helper. I'm not sure why. But
No. This is screaming.
why is it screaming?
Too many positional arguments for a method call.
do
Shouldn't be
you
screaming.
still need to call self in front of in order? Well, yeah, you do. Never mind.
Yep. Self dot left dot in order print.
Okay.
There you go. So that's gonna loop all the way down and recurse, and then it's gonna go all the way down and recurse some more. So remember, recursion is your friend, especially when you're dealing with all of these trees. In the GCA, you are definitely going to see some kind of data structure. It's either going to be a matrix, a tree. I had a matrix. Lots of people had trees, linked lists. Those things are going to be on the GCA. Why is
So
it still screaming?
basically, everything that we're going over, we need to make sure that we're good on it because it could be
Yes.
anything.
It could be anything. Why is it yelling at you?
Too many positional arguments for method call.
Oh, you don't have to pass anything in. I forgot that.
Okay.
For
Right,
some,
because we're calling it on self dot left, so we don't need to
Yep.
pass
There we
in
go.
self dot left.
bonk. Recursion.
Ooh.
So this recurses, and this one recurses, and in the middle it prints. There are some patterns to remember with the depth first and the breadth first. I think they were actually, for us, we actually had a little quiz and we had to pick which one was which. But there's print, recurse, 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 print, print, recurse, print, recurse. And I'm not the smartest person, so I always forget which one is which. All right, so let's scroll on down. We've got a beautiful in order print. All right. Nope, going up, going up. We've got a nice little search here. We have a depth first print, a depth first traversal.
And I think that's the code that she has further up in her notebook towards the beginning that we were working on after the group, after Josh had to leave.
I think
That
we were
was what he
working on-
gave us anyways.
I think we were working on breath first.
Oh, was it? Oh, okay. Yeah, it was. Okay, I'm sorry.
All right, so we get to use fun stuff.
Ooh.
What's the most fun thing that you can think of, Fatima?
Recursion.
We get to use recursion and also a stack. Actually, we don't get to use recursion. We get to use a stack.
I was going to say, does anybody see the word iterative in the problem statement up here?
We're gonna use a queue, and then we're gonna use a stack. How much fun is that?
So much.
I'm excited.
All the fun.
All right. So for our breadth first print, we're going to be using a queue.
Breath first or depth first?
The whatever one is first. I have the BFT on line 83.
Then it's on 130.
Yeah, that's-
We'll copy and paste. So we'll do that.
Yeah.
I have my breadth first as first, but if your depth first is first, it doesn't matter.
No, we'll do breath first. It's at the top. I just had it commented out.
Alrighty, so let's fix that. So we need to make sure that we have our queue imported. What can you tell me about the queue, Fatima?
Things leave from the start and they get added to the end.
Right. So first in, last out. Last in, first out. Doc, which way is it? You know, I know
For
you're
a
screaming.
queue, so imagine you're standing in a buying movie tickets. If it's first in, last out, then you're going to be really pissed because you're standing in the first position next to the window, and you're going to be the last person able to buy a ticket.
There you go. LIFO. Last in, first out.
No, first in, first out.
First in, first out. FIFO. Fee-fi, fo-fum. Okay.
I smell the blood of an Englishman.
All right. So we have our queue. We're going to take our tree. We're going to put stuff into the queue. And then we're going to print them. And because it's iterative, our poor friend recursion is so sad. No, wrong face, Fatima. Sad face. Sad face.
I thought this was very appropriate.
Sad face.
What have you got against loops?
Because I'm trying to make people love recursion because everyone's scared of it.
Oh, okay. Well, I thought for a minute there you were a data structure bigot.
No. Loops are fun, but we have to make people stop being scared of recursion. Recursion is our best friend. Not really, but you know, we invite it to birthday parties. Strange.
It's helpful.
Party.
It's helpful in solving code challenges.
Yes. So here we are with our breadth first print. First, we're going to have to make sure that we have our queue. So our queue equals. Oh, we actually have a class, a thing. We got to import. We have to. I don't know if you've imported it, but queue equals queue invoked.
Double check, see if we imported it above. It looks like it's not imported to this file.
Looks like you got to import it. I really hope it's easy to import.
You're in a different file, so no, it's not gonna be.
Is it just gonna be? Is it no? Is it from this? Import this?
You have to use the OS this in order to get it imported from another folder.
You know what? Why don't you just go copy the class of Q? It's short. So just copy this whole thing and paste it in there. You should be able to use import, but
Just gonna talk.
Yeah.
It's a pain. Actually, it's in there because we linked to singly linked list within that one.
oh no.
So you're going to go down a rabbit hole.
Wait.
All right. The queue is unfortunately necessary for the whole point of this is to utilize the queue.
Because I know we had that problem before.
Yep. Go ahead to the singly linked list and copy that in there too.
Oh dear. Oh,
Copy and
dear.
paste is bad.
This whole thing?
Yep, the whole thing, because the import structure is not something I want to troubleshoot when we have 4 minutes left. And include the node.
We're just gonna.
Yeah, we're copying like entire file structures. Just to save us from writing an import statement.
Those import statements are confusing. Like, let's just acknowledge that.
Put that before the queue. Because the queue references this class.
Okay, somebody needs to take on the task after this is over and before tomorrow of researching how to properly import things and bring that back to the class, because I'm not sure I can watch this.
I have in mind from queue import queue, and it doesn't work for the queue, but it does work for the stack. And that is the official point where I gave up on import statements. So now we're going to instantiate our queue.
All right, you guys have this in hand. I'll see you tomorrow.
All right, see you, Doc.
Bye, Doc.
Hi.
All right, and then we invoke it. So now we're going to add things to our queue.
How did that look?
So q.enqueue, and that queue, I believe your queue should be a lowercase q, but I'm not entirely positive with this particular way.
Would we just do
You
this?
just do
Follow it
new
on
queue.enqueue because you're already assigning to queue. Yeah.
There you go. Self. Perfect. So now with our breadth first search. So the first thing we remember is take a look at our queue and look at the values that it has. Look at the things that are inside of our initializer.
Size and storage.
Right. So we're going to be removing from our size. So while q.size it does not equal 0.
Okay, question.
Answer.
So self dot size, we didn't have it in the parameters for the queue.
You
Would
do
that come
not.
from the linked list? Is that where we got it from?
Yes.
Okay.
The queue has a size, and it changes based off of the what you're calling. So as long as everybody made everything appropriate, then this will work. So while our new queue size is not 0, so now we have to add things to the queue.
Right.
So
We're going to go through the things in the tree. So
print current. So first, current equals q.enqueue.
new q.enqueue.
Yes, I name mine q.enqueue.
Let's just do that.
Yep.
That seems easier. There is only one
But
Q.
then you might get confused.
I use the letter Q.
Even better. Nope, that's gonna attack everything.
Now that made Harry very upset that I named it the letter Q, but Harry's not here to yell at me this time.
He
All
can
right,
yell
so-
at you in the comments.
So then we have. All right, so Q dot in Q.
Q dot and Q. Why are these words so hard to spell?
Because it's a really bad word.
Okay.
So here we go. In queuing, we're just in queuing the Q. Current equals Q dot in Q. All right. Finding our data structure. Print current dot value.
So the value of the Q or the value of the new?
So you shall see in a moment. So so we have added our entire thing into the queue. We are enqueuing it. Here's the queue. Print the current value. There might have to be a DQ in here, and I literally made a typo in my solution code. Ha 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 ha. So now we're going to do the a breadth first search. So
Mhm.
inside of our while loop,
Right. We're in the while loop, and now what do we do?
so what do? Fatima, we found a node.
Okay.
And
we want
we've printed the
to-
value of the node. What do?
We want to print the value of the node to the left and the node to the right.
We don't actually want to print it. We want to
Queue them up.
Step over it.
Yeah, we wanna. So we're gonna queue it. So if current dot left,
It exists. Then
q dot in queue.
except now we're passing in current dot left.
Yep.
Okay.
And then our other if.
Current dot right. So if
Yep.
that exists, then in queue. And the word that is longer than it has any right to be. But
And has far too many e's.
no.
Ta-da! All done.
Is that the whole thing?
Yep.
What?
So, yeah, the thing is that the further you get into these patterns, the less code it takes, and the more braining is going on behind it. So let's scroll up and look at the in-queue, right? Let's just scroll up and take a look at what exactly that is.
I'll just
So we're creating a queue. We're initializing it, right?
mm-hmm.
And then we are passing everything into our queue. And we're increasing our size. So we're creating this list, we're queuing it up. Pack, 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 etc. Now let's go back to our binary search tree.
Mm-hmm.
All right. So we've instantiated it. We put it all together. This is going to be a queue. We have this tree. We're going to do a queue with it. So then while our size isn't 0, we're going to continue to add things to our queue.
Right.
until our Q is 0, basically. So we're going to add things. We should also be dequeuing at some point. This is the code, so this is how it works.
DQing.
I
There's
want
no
Dairy Queen.
DQs over here.
I really want Dairy Queen now. Why is this mad at you about this?
I'm not sure. It's saying assigning the result of a function call where the function has no return. Okay, so NQ never actually returns anything.
Try sorry, should have been DQ. That is where the DQ should have been.
So, well, that doesn't make sense.
DQ. There you go. So the DQ is returning a value. And that's what you're printing, and you're taking it out of your list. So first, we make a queue. And this is a structure that you're going to use a lot in your GS code thing. So first you're going to make a queue. And so if you're going to do this without using the fancy queue structure, you would make what's kind of like a queue.
A list?
Yes. So you would make a list. You'd add a whole bunch of stuff to the end of the list, which is, what's the function? To add something to the end. What's the built-in to add something to the end of a list?
Append?
Oh, append.
Right. So you would append this, and then how do we pop something off the front? It's not pop.
Remove?
Yes, you'd remove it. So you'd be removing something from the front and appending it to the back, and appending something to the back. And you would be shifty, 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 shifty in this manner.
Now, when they have you do the assignments and stuff on Code Signal with CS, are they looking like for a specific structure in your code?
No, they are only looking for, do you spit out the right answers and how fast is it?
Okay.
So there we go. We're taking our current, we're dequeuing it, we're enqueuing the left, we're enqueuing the right, we're putting everything in order in this list, and we're popping it off while we're doing it. So it's like we're putting stuff in just as fast as we're taking it out, and eventually we get to a value of none. So that is how that is working. And DQ, what does DQ do? It subtracts a 1. So that's how we're keeping this stable here. Everything clear on that? Fatima looks very thoughtful, very chin-strokey.
Wait, so over here on Q.NQ, we're enqueuing everything that they're giving us, right?
Yeah, we're enqueuing ourselves.
Okay, and then so over here we're going through the item one by one. And so, wait, so when we're passing in self, are we passing in just a singular node?
We're passing in the whole whatever they just passed us. It's probably a node. So we're passing in the self.
Okay.
Which has so if it's a node, what does it have?
It's got a value, a left and a right.
Right. Or in the case of a linked list, a
head and a tail.
Right.
Okay.
All right. So that is how we would do this iteratively in this kind of a structure.
Okay.
Make sense? Ish. All right, cool.
Yeah.
Depth first, print.
Fun times.
So now with a depth first, we are going to use a stack. And stacks are pancakes, right? Which means we add them to the bottom and we eat them all at once because some of us are hungry. Or we put it on the bottom and we pop it off the back. So, first thing we're going to do is...
We're going to make our stack. Do we need to go import stack from the other?
I'm going to go import stack.
We'll do that. Should this go at the bottom of everything else at the top? Or
yep. So we have our stack. the first thing we have to do is, why don't you look at our BFT and think about the DFT.
Like that.
Good.
And how do you add things to a stack? Push them on.
Very good.
So s dot push self into there, and while. Do we also have a size thing on the stack?
Mhm.
We have length. Great. So while s dot. Do we need to do that? Because
No.
would it just be size? Right. That's in the init. My bad. I was reading it wrong. It's not equal 0. Is it gonna be kind of the same?
Pretty much the same.
Okay. What makes it different?
The queue versus the stack.
Okay, just so the different ways that the queue and the stack work.
So a queue would go from the first to the last. And a
Mhm.
stack goes from the last to the first. So the order would be 1, 2, 3, 4, 5 versus 5, 4, 3, 2, 1.
Okay.
Okay, did you all copy the stack code in? I had to.
We did.
Okay.
Just at the bottom of everything else, we already copied and pasted to the top. My typing sounds fast, but is it fast? Not at all. There's just a lot of clicking noises.
Can you feed him his kidney food?
My typing right now is horrible because I'm not used to this keyboard.
I cheated through typing classes in elementary school. I would just look down very subtly at the keyboard.
Our teacher in elementary school would put a paper over our hands and blindfold us.
Well, y'all are making me feel extremely old now because I didn't have a computer in school until I was in like late middle school. So just hush.
My mother was a secretary in the days of punch card computers.
Oh
And
God.
yeah, she taught me how to type before I remember her teaching me to type when I was in like kindergarten. And
Wow.
it was brutal. Absolutely brutal.
We had fun computer games for it, but see, you got points for being faster, so we would all just kind of cheat to get more points.
I mean, she was brutal, but I'm a pretty intense touch typist. All right, so now we have done our breadth first and our depth first.
Mm-hmm.
Now we don't need these weirdo helper functions.
We just
Okay,
don't
so
need.
can you scroll back up real quick?
Yep.
Okay, so from the while loop is exactly the same. Why did you use pop?
Because in the stack we had created a pop function.
Oh, okay.
Whereas for Q, it was NQ and DQ. For stack, it was push and pop.
Okay.
What is it screaming about here?
So we added and we popped it off. So does that make sense? And how while is kind of the same as a recursion, except slightly different.
Yeah, I believe so. Yeah.
So they're the same, but not really. And the ways that are different are above my pay grade. But
wait, you're getting paid for this?
You guys should be getting paid for this. It's like 2-3 hours a day each for both of you.
Yeah.
You can buy us coffees. All right. So that does make sense though, right?
Yeah.
Mm-hmm.
All right. So now let's give this some zombie code. No more helper functions.
Okay.
That is completely reasonable, but this isn't recursive if it's not the same function.
Right.
And what is the thing that I want? I want everyone to be friends with recursion.
Oh, what
Mm.
is? Uh-oh.
Hmm?
I think I
I
just
should have
did.
probably marked everything else with that, but
I did.
We need to be friends with recursion.
okay.
Look at our pre-order depth first search.
Okay.
So, depth first means, where do we put the print statement? Look up, Fatima.
Uh,
Depth first. DFT. Look up. Up.
oh,
We're up. Where's our print
It's-
statement?
it goes in the middle of looking at the left and the right. Right?
Depth first.
Where am I scrolling up to? I've gone too far.
You're going. I scared you now.
Okay, it looks like the print statement goes in the middle of looking at the left and the right.
So we have a pre-order and a post-order, which is slightly different.
Right.
So means it goes at the top and the bottom. So pre-order goes at the top, post-order goes at the bottom.
Right. So before we do anything, before we do
So-
anything else, you want to print self?
So first we're going to check
If there's even anything.
if there's a self.
So if
Self.
do you want to do if not self?
Nope.
Or
If
if
self,
no?
because we want the function to run if self.
Oh, okay.
If self, print
Self.value or just
self.value. That's correct, because we want to print the value. You cannot print self.
that would just print the location, right?
It would print something that I do not understand.
So
Hexadecimal.
It comes out with this really weird like structural thingy. And the first time we all saw this in
No, you cut out.
with testing.
Yeah, there you are. You
you're-
were.
Testing. Aha, there we go.
Yes.
All right. The first time we saw it and then we tried to print, we all just kind of cried, and that was the day we looked up solutions on Google. So, if self, print self.value. You cannot print self has no value, alas. So now what do we look for?
We look to see if there's something to the left of self.
Yes.
So if self.left, then we want to run this whole thing again on self.left. So self
That's right.
left dot order
Dift.
dift. And then we want to do that again for the right.
Mm-hmm.
Okay. And then do we return anything?
Because we are printing. So the print is our return.
Awesome.
Because it wants us to print things in a pre-order depth first search.
Okay, so it's just going to print the values going through the depth first search.
That is correct. All right, so get rid of that post-order helper because it confuses me.
Right now. Okay, gotta stop doing that because we still walk through that in the video, so I need to keep this stuff for now.
I can't believe how cool that PDF viewer looks. All right, so now I want you to do the post order. Post being our queue, it means to do the printing last.
Cool. So
look at your pre-order and reverse engineer it. I'll wait.
got it. So first you want to make sure self exists. If self exists, then we do self dot left dot. Well, we check to see if self dot left exists. And then if self dot left exists, then we do self dot left dot post order diff. And then if did my tabs just get off? They'll just a teeny bit off. Okay. So then self dot left there, we do that, and then we check if self dot right exists. None of these are typing correctly. Oh. Self dot right. Dot.
No, you may not.
Sorry.
Okay, and then at the end of all of that, we print self dot value.
Yes.
Dot value.
Ta-da! So we're going to talk about the AVL trees because
Mhm.
I'm fairly certain you guys did not get to those.
No.
No idea what those are.
All right, cool. So let's go over to the AVL tree.
Is that the other file?
No, it's right here. We're just going to talk about that because we're a
Oh.
little ahead of schedule. We're just going to keep talking about these sorts of things because these are algorithms that you're going to need to use. And luckily, we don't have to import anything. So,
Ulterior motive.
so an AVL tree is balanced, but not necessarily in order. So that basically means that, like, so here we have a tree. It will always kind of look like this. So this is that, let's go with top, left, and right. And because I'm really bad at math, we're not even going to try and have me do these things. But if we turn this to the right, we still have top, right, and left. You get it?
Mm-hmm.
And then if we turned it again, we would have right.
And the one you have on the right, does the right not link to the top anymore?
It still does, but I'm trying to just, if I drew it, it would just be bad. We're trying not to make Ava draw too much.
So in other words, it's just like a triangle.
It is just like a triangle and it's balanced. So this is
Okay.
always balanced. This is the important thing to remember about the AVL trees is that they are balanced.
What
They're
does
not,
AVL stand for?
huh?
What does AVL stand for?
I don't know. Let me look it up.
Oh.
AVL tree. An AVL is a self-balancing binary search tree. It named for the inventors Adelson, Velsky, and Landis. That's why we don't need to know what it is. It doesn't tell you anything. It's just about these three dudes.
They just name it after themselves instead of making it self-explanatory.
Yep.
Thank
So we have a tree that balances itself.
Mm-hmm.
It is a binary search tree. Those whole things are kind of there, but it is balanced. So if we look here, we have the node, height, and balance. And our node has the key, our value, our left and our right. So if we scroll down, our display this is going to print out the display of the tree. And it's going to update the balance of height and update the balance and update the height as we go. So keep on scrolling.
So why is the height -1 and the balance is 0?
It has no balance and it doesn't exist.
Oh.
It says initialize height to -1 because of 0 indexing.
Mm-hmm. So if it had a height of 0, it would actually be a height of, how do programmers count?
1.
Yeah.
0.
So therefore, -1 equals 0 because indexing.
Well, I count in 0, so.
Yeah. So First, we're going to update the height of the tree. I scroll down to my height updater.
I'm guessing this isn't as simple as +1. But I'd like it to be.
Do you not have max depth first?
No, max depth does not exist.
All right, I have a little bit of extra code then.
Should we add it?
Yes, we should. I
Okay.
don't
Fair.
remember why. So, this is the max depth. It finds the number of nodes along the longest path from the root down to the farthest leaf node. So define max depth self. If not self.node, return 0.
So if not self, then return 0.
So we're going to instantiate left depth equals -1. And go ahead and guess, Fatima.
Right depth.
At
Can we also put it at -1?
yes. Why do we instantiate it at -1?
Because that's the equivalent of 0.
Yes. Because of 0 indexing.
Got it. Okay.
All right. Next. If self.node.left.
Self.node.left.
Yes. If self.node.left.
Okay.
Left depth equals
+1.
self.node.left.max depth.
What?
Self.node.left.max depth.
Yes.
Invoked.
Invoked.
Okay.
I'm
cool.
glad
we
you
are-
understood that.
Because we are.
Recursion. Woo.
Yay, favorite. Okay. If self.node.right.
Okay.
Guess.
Right depth equals self.node.right.max depth, and then invoke it.
Right. And finally, if left depth is greater than right depth.
Greater than right depth.
I am looking at the wrong thing. If left depth greater than right depth, return left depth +1.
Okay.
Else guess.
Return right depth +1.
Yes. Because AVL trees are
Balanced.
good. All right. Now let us move on to update height.
Okay.
Yeah, I'll definitely be catching up with your code.
So we are going to use our friend. Not recursion, but our new friend that we just invented. Hello, sweet baby. Did you eat everything?
I haven't eaten
Aw.
yet.
So our update height, if not self.node,
If not self.node. If no self.node.
what do we return?
We're returning nothing. Just ending the function.
In this case, we're returning 0.
Right.
Self.height equals
0.
self. Max depth. This is our helper function that makes our life easier. So our update height is going to, you add something to the tree, then the height goes, oh gosh, where is it? Find update, check. Okay,
Okay.
all done. Next,
Update balance.
update balance. Good. Balance equals self.balance. So now we're checking for things to be balanced. So if self.node.right and self.node.left
Uh,
balance equals self.node.left.max depth minus self.node.right.max depth.
yes, but it's supposed to be something up here, I'm guessing.
Balance equals.
Got it.
So now we're going to the line 72 with an elif or an elif or an elf, as June likes to put it. Elif self.node.left and not self.node.right. Balance equals
Balance equals.
yes.
Are we just going to reverse them or just leave it as self.node?
Self.node.left.max depth.
Node dot left dot-
Elif.
Oh, I'm guessing that this was supposed to be up with the elif statement, and I decided not to do that for whatever reason.
Yes. Another elif.
Mm-hmm.
Yes.
It's going to be the reverse, so self.node.right and not self.node.left. And then balance will equal self.node.right.max depth.
Will equal 0 minus self.node.right.max depth.
So close.
So close. Full disclosure, my mentor helped me come up with this stuff because this one was beyond me at the time and is still kind of beyond me.
So then,
Our
okay.
final thing that we do is
Return
we're going to set self.balance equals yes. So again, checking through all of this, we see that helper functions in recursion are our friends. When you're working on the GCA or when you're working on your code signal problems, sometimes you do need to write an extra function. Sometimes that's there. You don't have to do it in one function call. You can use recursion, you can use methods, you can use whatever. It's limitless. Okay? So if you're in a for loop and you realize that like something would be a lot easier if you called a method for everything and just like saved that and then did something else and returned the value, do it by all means. There are times where you're going to think that that is going to be the better solution. So don't be afraid. Are you afraid?
No.
Good. Good, no fear. Onward.
Okay.
So now that we have our update height and our update balance, we are going to do our left and our right rotation. And I'm not going to lie, this one was actually on my GCA.
Hmm.
And
So what would be the point of doing these rotations though?
I have no idea, and Doc is not here.
Okay.
No practical application then, it's just there.
I think that you rotate the tree to add a node to it in order to keep it balanced.
Okay, well that makes sense.
I think that is what you do. I could be horrifically incorrect.
Shouldn't it already be balanced? Or-
Not yet. We're balancing it.
Oh.
So we're going to rotate to the. So we're going to rotate it to the left. So, first thing that we have to do is check.
If self exists. I feel like that doesn't work.
So, in this particular case, we're going to check if not self.node return.
Not self done. I was thinking, if self is probably a little too simple for what we want it to do. Okay.
So, now remember how we had to do all of those terrible reassignments?
We're gonna have to do that again, reassign every corner of the thing and then shift it.
So, we have this one and this one and this one. And so we're just gonna.
Is that to the right?
Or, the other way too. So
We need
Self-
to store all the points and variables before we start.
self.node.right equals self.node. Self.node equals self.node.left.
Node right equals self.node.
And then self.node equals self.node.left. So we're just rotating it one. We're not rotating it in a circle. We're just rotating it one.
And since this is the order we did it in, we don't have to reassign them to other things first.
This would rotate it in a, yeah, that's right. That's fine. Self.node.right. I gotta draw it. Self.node.right. Okay.
Self.node still equals itself. But would self.node.right need to be something else? Because self.node.right equals
Self.node.right.
self.node at this point.
So self.node.right equals self.node. So this one has been moved. Self.node equals self.node.left. And then I think this one just stays in the code that I have is 2 lines of code.
How?
Because we're only, because of, I don't know. But it passed the tests, which is why it confuses me a little bit right now.
But what about those hidden tests they talk about?
All I'm going to say is that I have 2 lines of code and it passed all the tests, including the hidden tests. But I don't know why, and I'm kind of confused because I really should have written a comment here. Jess, you were right.
I'm a little confused by this because, okay, so I know we're assigning self.node.right to be self.node. Self.node is still what it originally was, so it's okay when we change it here and like etc. But when we get to self.node.left,
We don't need this line.
We just straight up don't need this line.
Yep. Because you're shifting it.
But what happens to self.node.left?
That's why I'm actually staring at my code right now, trying to figure that out. Because I remember this passed, and I was really confused by the fact that it passed. So self.node.right equals self.node. My love, can you please open your Python folder? Did you complete the AVL tree? It's in data structures. All right, so let's pretend that this is all we need and that my brain is working fine. And write the right rotate.
Okay, so it's just going to be the reverse of that.
Yes.
So if not self.node, return self dot node dot left equals self dot node right
The left child of the node, the parent. Let me keep
and
the old right,
self-
old parent. Because we're only reassigning two things. That's why making the left child of the node the parent and make the parent the right child of the new parent. That's all. So that's why it works, is because we only have to assign two things.
So what does it automatically push the third out and into the next one?
This is what it asks us to do. Make the right child of the node the parent, and then make the old parent the left child. So they're only asking you to change two things. They're not asking you to change the third.
well, why? I know you didn't design it, but like,
Yeah.
That is what it is. Why is the sky blue?
that's because of molecules in the air
Yes.
that bounce off.
Yes, so that's why we're going to go with this, is because molecules. This is probably one of those like weird 3D things.
I'll check out. Wayne linked a Crash Course video. I didn't know Crash Course did computer science, so that's awesome.
Yes, they do Crash. Crash Course does everything.
Mhm.
They're only asking you to change two things. So in theory, think about it like this. It shifted it like this.
Mhm.
That's more like what it did. It left one thing in place and
Oh, okay.
shifted the other two around it. It didn't turn the whole structure. It rotated on the node.
It was like, if this is a triangle, it just went from being like this to this.
Yeah.
Yes. That's
Okay,
why.
that makes more sense.
It didn't spin it in a circle.
Rotated on a point.
It rotated on a point. There we go. Now our
You
brains are
need to
working.
get some like animation yeah, that thing.
Annotators. That would be great if I could code that. All right, so now we have rebalance.
Uh-huh.
Oh God, why did I write all of these? We could have just been done, but no, I had to be extra and do the stretch goals.
Hey,
All right.
stretch goals are never bad.
Isn't this great, Ava? We're all understanding it so much better because you went the extra mile, and we all appreciate you for it.
All right, so rebalance.
Mhm.
First thing we're going to do is declare the tree height. What is the easiest way of getting our tree height?
Max. Depth.
Mhm.
Yep, so tree height equals self
Self dot.
max depth.
Ooh, no, it's depth.
Max depth. All right. Then if, oh jeez, if tree height is greater than 1 and self.node.key is less than self.node.left.node.key, self.right.rotate.
I wasn't able to keep up this time.
Okay. If tree height is greater than 1 and self.node.key is less than self.node.left.node.key,
Yeah.
self.right.rotate.
Self dot node left node key.
Yes. Self node left node key. Self right rotate.
Okay, you're gonna have to explain this one out.
Okay.
This is us forcing it to balance for some reason. I just don't know how.
So if the tree has a height of greater than 1
Mhm.
Yeah.
and self.node.key, which is basically going to be our value. So self.node.key is less than self.node.left node key.
Okay, okay,
Oh, is
okay.
that because the
Okay.
greatest thing needs to be on top? So we're just gonna flip it.
In a AVL tree,
Or wait, no, the thing to the left always needs to be smaller than the top thing.
we're going to try and keep it balanced. And we're also going to try and keep our structures like so. So this would be a bad thing, but we want to keep it as balanced as possible. So it kind of goes in like a weird circle tree. So else if tree height is less than -1 and self.node.key is greater than self.node.write.node.key.
I think we have typos galore. Oh, no typos.
So if we rotated it to the right, what are we going to do now?
Left.
All right, now is where you're going to start hating me. New line. Else if tree height is greater than 1 and self.node.key is greater than self.node.left.node.key. I remember Harry had to explain these. Self.node.left.left rotate, self.right.rotate. Self.node.left.left rotate.
Why-
And
Oh, never mind.
And self.right rotate. So it goes eh, eh, eh.
okay.
So it's kind of like a weird circle thing. Imagine that we have like something like, I'm bad at drawing. Why do I think I can draw? So we have things where we need to fill in here. So it just kind of
Kind of reminds me of the jack-o'-lantern that my boys carved when they carved their first pumpkin.
I try so hard.
No, I'm messing with you.
Else if tree height is less than -1 and self.node.key is less than self.node.write.node.key.
Self.node.write.node.key.
Yes. Then self.node.write.right rotate, self.left rotate.
Is there like some more in-depth documentation on this?
Yes, I invite everyone to use the Google.
Use the
I
Google.
use the Google. There are some really great videos and visualizations that are out there that I'm kind of tired and don't feel like Googling. But there are some really good. I was prepped to do iterative sorting, guys.
Sorry.
Josh. It's all good.
We spent so long, and it's not a bad thing, but just spent a really long time trying to figure out depth first traversing.
Yeah.
This is why you have your solution code for class, y'all.
I think we took the solution code straight from Canvas, but that wasn't class based or
Yeah.
whatever.
Yeah, no, don't use the canvas. So our final, we're going to insert
Ooh,
into the tree.
okay.
All right. And then we're going to talk about this a little bit and get a conversation going. So, if self.node,
Self.node. So we're checking to see if it exists.
yes.
Why would I invoke it? I don't know.
If key is less than self.node.key,
Where are we getting the variable key from?
key is
Oh, we passed it in.
yeah.
Okay.
If not self.node.left, self.node.left equals AVL tree node key.
Yeah.
AVL tree invoked node.
Dot node?
No, pass in node.
Oh, okay.
No, pass in node. The class node.
And then dot key, right?
No, we're going to pass in key. So we're going to pass in node and then pass in key. Inside the node. There we go. So we've
So now-
created
you got key on the insert as a parameter, but you don't have it on the rebalance. So where did the key on that one come
We're working on it.
from? Oh, okay.
So this instantiated a node on the tree.
Okay.
So if the key is smaller than the current node that we have passed in, and there is no node on the left, put the node on the left of the tree. Got it?
Okay.
Else,
Else on which level?
the current level.
Okay, cool.
So if there is something there, then we need to
Recurse.
good self.node.left.insert key. And I hate writing class-based structures because I start doubting my sanity. So
Mm-hmm.
Those
else.
hypnotizing things, and you just keep going deeper.
Yeah.
So now we have an else. Good. If not self.node.right,
Not self. Node. Right. Then just the reverse.
Mhm.
Not self on node right. Then self dot node right equals ABL tree node key. And then the else statement, and just do self dot node dot right dot insert key.
perfect. And then our final else. Self.node equals node key.
Like that.
Just like that. All right. Everyone have a headache.
Yeah.
Just
Yeah.
Okay. So an AVL tree is a self-balancing search tree. A binary search tree has a point at the top. It has a left and a right. It has a left and a right. It has a left and a right. It is inherently bottom heavy.
Yeah.
Have you guys ever crocheted a circle?
No.
I knit. I don't know how to crochet.
It might work the same in knitting. You guys use the circle. No, it works the same. Kind of works the same. Have you guys ever seen a basketball?
Mm-hmm.
All right. So a basketball's got these like triangle-y bits on it, right? Or seen a baseball where it's got these like little bits of this is how you sew a circle. This is how I would sew a circle. I'm not good at drawing. So there is a node. We can kind of rotate within this. It's balanced. Can you think of it that way?
So
Okay, so there's triangles coming off of the node going in all directions.
Yes.
this looks like the node has more than one left and more than one right.
Just go with the analogy.
Okay. Cool.
Just go with the analogy. The idea is that this whole structure is balanced. I'm thinking of that little thingy that goes shk, 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 the little connects thing that you have.
Yeah.
That
I know what
thing.
you're talking about.
And it's got all these little triangles.
Mm-hmm.
And they can rotate and they grow and they shrink. And that's kind of the idea.
Oh, like the ball one?
Yeah.
That's like
So we have these nodes and they can grow and grow and grow, but it's kind of like a sphere. It's not a sphere. But if we can think of it that way, it rotates, but it doesn't rotate perfectly. It shifts so that okay, so when I would get bored in school, I would draw these little patterns like this.
Mm-hmm.
And I would try and see like how balanced I could make it. And that's kind of what this thing is trying to do. You guys kind of see with the left and the right and Ava's terrible artwork.
Hey, it looks good.
So do you get this? It's, of course, I'm not following an actual algorithm, but this
Like
is
a golf ball.
Yeah, a golf ball, a triangular grid thing.
Yeah, like when they build the golf ball houses. That's how they build it.
Yeah. So kind of like this. This is kind of like what it's doing, and this whole structure rotates until it has an open spot that would keep it even.
Okay.
Now, it's not really shaped like this, but this is kind of the idea. Whereas the binary search tree is on the bottom, and the bottom of the binary search tree can just be massive, and the top is always the center. The AVL tree is not really like that. It's kind of like, and we have like our linked list that only looks to the right. And then we have our doubly linked list that looks both directions. We have a binary search tree that says a little thing up here and is super huge at the bottom. And then we have our AVL tree, which is a really weird shape named after three dudes. So that's kind of how we can think of it if it helps you to like visualize as something.
Kind of like multiple binary search trees in a ball.
Yeah. Kind of like.
Yeah. Just like hash tables are kind of like linked list, right?
I would not say hash tables or anything like linked lists.
Or no, I'm sorry. Hash tables are kind of like arrays. That's what it was that you
Hash
said.
tables are kind of like dictionaries. Linked lists are kind of like arrays.
Okay.
Kind of like. They are not the same, and I will get in trouble for the rest of my life if I say they are. But if it helps you to conceptualize, they are kind of like. I'm sure that there's a video title where it's just like Ava says kind of like for 45 minutes straight.
Thank you for the idea.
When you get your certification, we'll just post that and tag you on LinkedIn.
Like,
Thank you
kind
for all of the wonderful hours tutoring.
of kind of like the Ava kind of like Harry's going to yell at me, but I don't think Doc would approve of this, but compilation.
I might like have to take just that one section and turn it into its own video.
So these are these are things that are kind of like other things. It helps to conceptualize it in that way because on the code signal tests or the code signal tests, there will be times where you'd be like, oh man, a linked list would totally work here. If I could only make a queue. Oh wait, what is a queue? Kind of like a list. Oh wait, what's a stack? Kind of like
Pancakes.
and also lists. So that's like the things that you have to be able to think about. Believe it or not, I actually used a cache, which is something we're going to talk about this coming week in my backend today. I actually used a cache, also known as a hash table. And because I know what a cache is basically kind of like a dictionary, I was able to do a quick and dirty implementation that saved my code time. And the more of these that you write and the more you wrap your brain around them and you can see the solutions side by side with things that like actually make sense, the more you can in fact think of those things. Like as I said before, regards to looking up answers to the elite code solutions. Don't reinvent the wheel if you're studying. Come up with an answer, like work hard, find your answer that is yours, and then look up an O of N answer and see what data structures they used. See what the people who are smarter than you did. And if you can understand why that worked, then the next time you see that particular algorithm or an algorithm that's like that algorithm, your first thought might actually be, oh yeah, I remember this dude used a cache. Oh yeah, I remember if I instantiate here, it makes this better. So while I don't encourage Googling the answer for the homework, totally look it up after the fact. Look it up and see what the smarter person did. Because
Yeah.
it is a legitimate way to learn.
Or you might be able to also find an easier way to do it where you have less code.
Yeah, exactly. When I was in college for music, for opera, it was really funny because when I started college, we were told over and over and over and over again, never, ever, ever listen to a recording. If you're learning an aria, don't listen to a recording because it's not going to be your interpretation. And then by the time I graduated, I had like masters from all sorts of places say, "Why? Well, whose recording did you listen to? Who are you listening to? Like, what recordings are you using as the basis for what you're doing?" So, in the great like spirit of all of that, don't use a recording, but listen, find something.
Is it?
Don't copy what they did, understand it,
That sounds like
which
a
was the point that
little
the
bit,
teachers were making. A little bit the same,
a
a
little
little
bit like
confusing.
the idea.
Don't
No, a little bit like the idea that there's no such thing as an original story, like at least in a book.